Okay, first of all, I apologize in advance for the quality of the video, particularly the focus. It's the best I can get my little webcam to do. So we will do what we can here. I guess it's better than nothing. All right, so number one is given the graph of f prime of x, so this is the graph of the derivative, sketch a graph of the original function. Okay, so there's several different ways that you could approach this. I think maybe the most straightforward, you're probably pretty comfortable at this point, or hopefully, with making sign charts. So if you've got the graph of the derivative, you can actually go ahead and make a sign chart for both the derivative and the second derivative. Now, keep in mind that this is the graph of the derivative. So when you're making a sign chart for f prime, you're literally making a sign chart for this graph. The graph is positive when it's above the x-axis, and it's negative when it's below the x-axis. So the first derivative is negative up until -2, and then the derivative is positive between -2 and 0, and then it's negative again between 0 and 2, and then the derivative is 0 at x equals 2 because it's hitting the x-axis, but then it's negative again between 2 and 4, and then after 4 the derivative remains positive for the entire rest of the function. So knowing where the derivative is positive and negative will tell us where the original function is increasing and decreasing. Okay, we can also make a sign chart for the second derivative. Now, since the graph that we have is of f prime, then the second derivative is the slope of this graph, since the second derivative is the derivative of the first derivative. Okay, so at first the slopes are positive all the way up until -1. So that means the second derivative is, oh really, come on, let's see if we can get it to focus back here. All right, there we go. That's probably going to happen lots in all of these videos. Just stay patient. I will try and do the same. Okay, and then between -1 and +1, the slope of the derivative is negative, which means the second derivative is negative. And then the slope becomes positive again, so between 1 and 2, the second derivative is positive. And then the slopes are negative between 2 and 3. And then the slope is positive again between 3 and 5. And then after 5, the rest of the slopes of this graph are negative. So lots of potential inflection points where the second derivative is changing sign, so or where the function is changing concavity from concave up to concave down. Okay, so with this information, it gives us enough to sketch a pretty good idea of what our original function looks like. So we'll go ahead, we've got something happening pretty much at every integer value, -1, -2, 0, 1, 2, 3, 4, 5. All right, so now sketching a graph of the original function. All right, so something to keep in mind, the domain of the original function. Well, if you look at the graph of the derivative, the domain of the derivative is all real numbers. So if the domain of the derivative is all real numbers, the domain of the original function also has to be all real numbers. Because if there was a place where the function didn't exist, the derivative wouldn't exist there either. Okay, as far as where we start this graph, high up on the y-axis or below it, we don't have any other information. We don't know any x-intercepts. We don't know any y-intercepts. We don't know any actual points on the function, which means the shape of the graph could be anywhere. It could start above the x-axis. It could start below it. So the shape here is the shape, and the increasing and decreasing is what's important. We don't know exactly where this is going to be located on the y-axis. That's okay. All right, so from -∞ to -2, the first derivative is negative, the second derivative is positive. So we are decreasing and concave up. So decreasing and concave up. Between -2 and 1, between -2 and -1, it switches to increasing, but it's still concave up. So we've got a local min at x equals -2. Between -1 and 0, let's see, between -1 and 0, we're still increasing, but we've switched to concave down. So there's an inflection point, still increasing, but now we're concave down. So there's an inflection point at x equals -1. Between 0 and 1, we switch to decreasing, but we're still concave down. So decreasing and concave down. So there's a local max at 0. Between, oops, I labeled that wrong. That's a 2, and that's a 4, and that's a 3. Okay, so between 1 and 2, so let's see, we're still decreasing, but we switch to concave up. So we're still decreasing, but we've switched to concave up. So there's an inflection point at x equals 1. And then the slope at 2 is 0, so this is going to level out. And it's still decreasing, but it switches to concave down. So the slope levels out to 0, and then it's decreasing, but then it's concave down. All right, between 3 and 5, we're still decreasing, but it switches to concave up. So we've got another inflection point at 3. From 4 to 5, we switch to increasing and still concave up, increasing, still concave up. So there's a local min at x equals 4. And then after 5, we're still increasing, but it switches to concave down. And there's a graph of the original function.